All right, here for a recording on the RAAS, renin-angiotensin-aldosterone system. We're going to tie that into blood pressure regulation. This particular video is going to focus on the angiotensin II component of it. Okay, so the overall, the renin-angiotensin-aldosterone system has as its overall effects an increase in total peripheral resistance and an increase in blood volume. Now, I'm squeezing this up at the top. I'm going to get some anatomy in here in a second. If you recall, if we solve Poiseuille's equation, usually solve for flow, if we solve it for pressure, and we use the whole system as our model here, the entire cardiovascular system, then blood pressure equals cardiac output, flow. So pressure equals flow times total peripheral resistance. Right? And so what we need to do is see how the renin-angiotensin-aldosterone system, specifically in this video, angiotensin II, contributes to what we'll find is directly to an increase in peripheral resistance and indirectly to an increase in blood volume. Okay, now before we jump into angiotensin II and how it's produced and where it comes from, let's make sure that, because this one's easy, right? This guy, I should have reordered them, is right there, right? So it's easy to see how changing resistance will change pressure. And again, we'll get into the mechanism of that. It's pretty straightforward. It's affecting the vasculature. But what we need maybe a better understanding of, or at least a review of from previously, is how blood volume affects cardiac output, right? And by affecting cardiac output, it's going to affect blood pressure. And so if we write that out, we're trending towards an increase in blood volume with stimulation of the RAAS system. So if we get an increase in blood volume, we're going to get an increase in central venous pressure. And again, the rationale for that, so let's draw that out. Central venous pressure, CVP. And the rationale for that is that the veins are the high compliance vessels in the vascular circuit. By high compliance, we mean they have the smallest change in pressure when there's a change in volume, which is what we want to occur if volume changes, right? You drink a liter of water, you don't want your blood pressure going up by 50%. And so that extra volume, a large component of it, will end up in the venous circuit because of high compliance. Right? So compliance, I don't want to squeeze it on here, but compliance equals the delta P over delta V. In other words, the change in pressure that occurs with a given change in volume. And so high compliance in the venous circuit means that our central venous pressure is going to go up. Now, it's not going to go up as much as it would, if you squash that same volume into the arterial circuit, which has much lower compliance, which means the pressure would spike much higher with a given change in volume. So because this is the region of, if quote unquote, give in the cardiovascular system, most of that volume will be in the venous circuit, and it will increase the pressure there, again, less than it would anywhere else, but pressure there rises. Because that pressure rises, we've now increased the linear pressure gradient from the large veins, central venous, right, into the diastolic heart, the heart in between ejections. And the pressure in the heart is usually very close to zero. Right? And so the bigger the central venous pressure becomes, higher the central venous pressure becomes, the bigger the P1, P2 difference becomes, P1 being central venous pressure, P2 being the, call it atrial pressure, that's the first chamber that the veins are going to dump directly into. If that gradient gets bigger, then our venous return will go up, right? Pressure drives flow. So because central venous pressure goes up, we get an increase in venous return, VR. Because we get an increase in venous return, we get an increase in, as I just mentioned, diastolic filling. So we're going to get an increase in EDV. Now I'm going to put that synonymously or simultaneously, maybe is a better way to put it, simultaneously with a decrease in ESV. All right, let me remind you, end diastolic volume, that's the volume of the ventricles at the end of their diastolic filling period. If the pressure gradient driving venous return goes up, they will fill more, right? So EDV will go up, right? Now, ESV, and I can have this, you know, as an arrow to this. Let's do that. Right? And the rationale there, that's the Frank-Starling mechanism, right? That's the length-tension relationship of cardiac muscle, striated muscle in general, but when you use the Frank-Starling term, then it's for cardiac muscle. And what it means is that the more you stretch cardiac muscle up to a point, the more you optimize the overlap of the myosin and actin filaments, the more cross bridges you get, and the harder the contraction becomes. The harder the contraction becomes, the more blood volume you eject, right? Which means that end systolic volume, the leftover volume after ejection, will go down, right? The difference between EDV and ESV is stroke volume, the volume you move with each beat, each contraction of the heart. So EDV went up, and again, at least potentially, ESV is going to go down because we're going to contract harder because of the Frank-Starling mechanism, right? And that, of course, is going to make cardiac output go up. Like, oh, so this overall. And, ta-da! There we go. Now we have directly tied our change in blood volume to a change in cardiac output. And of course, the change in cardiac output is going to lead to, this scenario up, is going to lead to an increase in blood pressure. Okay, so again, we're going to follow up more, we're going to look at angiotensin II more directly in this video. We'll follow up with the aldosterone and ADH sort of component of this system in separate videos. And those are going to be tied more to the blood volume explanation I just gave you. But I wanted to pull it all together now so we can see how the system as a whole is going to affect cardiac output and total peripheral resistance to, in a compound fashion, at least additive, if not in some ways synergistic, on blood pressure control. Okay, so now we need to see where angiotensin II comes from. So we need a little bit of anatomy. So I'm going to draw, I'm going to exaggerate some parts of this and leave others sort of reduced. So my green pen is working today. Bad. Okay, so we've got an exaggerated renal corpuscle, and then the rest of the nephron here is sort of minimized in size relatively, so we are not to scale here. But so what we've got, again, to remind you of anatomy, we're going to have our blood flow in vessel here, right? We're going to put a couple labels on here. I'm sorry, these are small, but I have a lot to sort of squeeze in here, so we'll call this the EA. For the efferent, sorry, did I just say E? Sorry. Afferent arterial, E for exit. Afferent arterial, that makes this the efferent arterial. Right, the afferent arterial leads to the glomerulus. That's this ball of capillaries. That's where filtration occurs at the kidney. Right? And again, you have 2 million of these total in kidneys, 2 million plus. And so this is happening over and over at many, many different locations to generate the net total filtration of, I'm going to put a number on it again because we need sort of proportions here to sort of understand, but we're going to generate about 180 liters per day of filtrate, right? So that's being filtered into, that's called Bowman's capsule, if you recall, right? And again, just to review the anatomy of the nephron here. So it's the real corpuscle is the glomerulus, the capillaries, plus Bowman's capsule, right? I don't have room for all these labels, right? Glomerulus plus Bowman's capsule. Bowman's capsule collects the filtrate across the filtration membrane, this combination of the glomerular capillary wall and the inner layer of Bowman's capsule there, the green. Filtrate moves off into the proximal convoluted tubule, from there into the descending and then ascending loop of Henle. If you recall, that formed the countercurrent multiplier. It's essential for some functions that we will probably bring into another video, but generates a solute gradient in the interstitium. The ascending limb of the loop of Henle leads into the distal convoluted tubule. The distal convoluted tubule, and actually several of them, I've got some others coming in here, drain into the collecting duct, right? And so it's PCT, the loop of Henle, DCT, and then the collecting duct. So at the bottom of the collecting duct is where we release urine into sort of the open spaces inside the kidney, which eventually collectively drain into the ureter. Ureter leads to the bladder, right? And so the collecting ducts are sort of like the final processing site for the production of urine. Okay, now something really important to point out, though, with regard to this whole angiotensin thing, is that very beginning, if you want to call it the end of the loop or the beginning of the DCT, kind of at the junction where the two sort of meet, right about here, at that dashed line, that actually sits, so this is not anatomically correct, back here. In other words, this sort of has to fold back on itself to be anatomically correct. So the beginning of the DCT passes through what's called the vascular pole between the afferent and the efferent arterioles. All right, so let me add that. Right, so this is sort of piece of the DCT here. I'm going to give it some wall thickness. Now I'm going to put some, looks like spokes basically, right? But those are what I've divvied it up into is the cells that form the wall. So it's a simple layer of cuboidal epithelium, right? And if I had room, I could squeeze some, I know you probably can't see these, but I'm just putting nuclei in there so you can sort of know that these are the cells that are forming the wall of the tubule. So in this piece of the tubule is going in and out of the paper here, right? As opposed to sort of the surface view of it over here. Okay, now so I've got it cut so that you can sort of see the inside of the nephron, which is actually over here. Right? Well, again, this is over here. Okay, so that is called, that region of the DCT, the early DCT, is called the macula densa. Right? That's this guy. So those cells at that particular spot are called the macula densa cells, and they are a sensor, which we'll get to in a second. Now, I have to say a little bit more about the afferent arteriole, because it has specialized cells in its wall. I'm going to exaggerate them a little bit here. Actually, I'm going to color them in so you can maybe see them a little bit better. And of course, the wall, it's an arteriole, right? So it's made up of smooth muscle and a lining, endothelium, and all that. I'm not trying to show you all those details. But it's got specialized muscle cells that are actually enzyme secreting. So those are called the juxtaglomerular cells. I'm going to abbreviate that as the JG cells. So the JG cells produce renin. Right? And again, renin is not a hormone. Renin is an enzyme. And so renin is going to act on a substrate. But before we get to that, let's look at the stimuli that are, well, let's do the pathway to get to angiotensin 2. Then we'll tell you what stimulates these JG cells to produce renin. And so let's put it'd be easier if these words didn't have so many letters in them. But angiotensinogen is a precursor molecule. So it's a prohormone, right? That circulates, it's produced by the liver, and it circulates in the plasma and is inactive. Renin acts on angiotensinogen to cleave, and this guy is big, but what it's going to do is it's going to cleave a decapeptide, a 10 amino acid sequence known as angiotensin 1, which we'll abbreviate as ANG1. So renin, right, put a plus sign on it, right, stimulates that not conversion, but a cleavage of the angiotensinogen to release angiotensin 1. Angiotensin 1 is largely inactive. I mean, there's a lot of studies that show that it does some things here and there, like experimentally, but most of them are not thought to be physiological. So this is largely a intermediate, right? Again, still a pro-hormone, really, because it doesn't have effects of its own. And it is going to be converted pretty much automatically, without any real control, into angiotensin 2. So basically what we do is we go from a decapeptide to an octapeptide. So we just, this enzyme, another enzyme, cleaves those 2 amino acids off of angiotensin 1 to produce angiotensin 2. Angiotensin 2 is our active hormone. This enzyme, right, is called angiotensin converting enzyme. There are actually antihypertensive drugs that block this enzyme, which make a lot of sense given what I told you at the very beginning, which is that our angiotensin system is going to lead to a rise in blood pressure, right? And so ACE, angiotensin converting enzyme, is found on endothelial cells, especially in the lung. And all of our blood passes through the lung circulation every 60 seconds or so. And so it's a very effective way to rapidly convert angiotensin 1 into angiotensin 2. Now, the angiotensin 2 has sort of a multitude of effects, right? And so I guess we'll follow up on that, and then I keep getting ahead of myself here. Now we have the angiotensin 2. Okay, great. So we'll follow up on the effects of that in a second. But let me show you what the stimuli are, and some of these should be obvious. So in other words, we know that this guy is going to lead to an increase in total peripheral resistance, and then indirectly to an increase in blood volume, both of which are going to lead to an increase in blood pressure. So guess what? The afferent arteriole is a baroreceptor, right? The JG cells themselves sense mechanical stress in the afferent arterial wall. And they are more responsive when that stress is low, right? Because low stress, distension of that wall, would indicate low blood pressure, and we would need more angiotensin 2 to do more of this and boost that blood pressure back up. So we're going to have low BP as a stimulus to the JG cell secretion, right? Now, in addition, there's another indirect, well, there's two actually. When your systemic baroreceptors, right, pressure receptors in your aorta or your carotid sinus, when they sense low blood pressure, your sympathetic output goes up. That should make sense, right? Sympathetic output increases cardiac output, causes vasoconstriction. It can cause vasoconstriction, especially when that sympathetic output is very high, right? And we already said how that will affect blood pressure. So guess what? Increased sympathetic output stimulates renin, stimulates the JG cells to produce renin. Again, a multifaceted, sort of integrated response to helping boost blood pressure when blood pressure is low. Now, when blood pressure is low, so this pressure is low, what's going to happen is the filtration rate at the glomerulus, all of them, will fall, right? That's called GFR, glomerular filtration rate. And so you will no longer be, at that moment, be filtering 180 liters per day. You would be less effective at excreting the wastes from your blood plasma, right? One of the basis of how our kidneys work is they produce a very large filtrate and then reabsorb an enormous percent of that, except the waste. I mean, an enormous percent of the water, an enormous percent, 99 plus, right? 180 liters a day. You probably excrete about 1.8 liters per day, right? And so a 1% of this very large volume of filtrate, a very large percent of it is reabsorbed, leaving a very small percentage of it to carry our wastes and excess water, like a small amount, out of the body every day. Okay, so, but if pressure falls, then GFR falls, then we have a smaller filtrate, and we're going to be a little less effective at excreting our waste. So GFR is very well autoregulated, meaning we don't really let it fall from whatever our normal value is, again, somewhere in that ballpark, every day. And so what's going to happen is, if it does fall, the transport mechanisms in the nephron, they're sitting there doing their thing, right? It's like factory workers on a conveyor belt, right? If all of a sudden the conveyor belt, like, so let's say the factory workers are pulling off sodium molecules, right? The transporters are pulling off sodium molecules or glucose molecules or whatever molecules, right? If all of a sudden they slow down the conveyor belt at the factory, right? The factory workers are going to be more effective at getting the solutes, right? The substances on the conveyor belt off of it. And so what happens is the tubular fluid osmolarity falls, right? The flow rate goes down. Come back to the macula densa. Guess what? The macula densa has what's called a primary cilium, a single stereocilia that sort of projects off of those cells into the lumen that's a mechanotransducer. It's detecting flow rate. And if that flow rate falls, it's an indicator that GFR has gone down. In other words, we're reabsorbing more effectively, and which usually occurs because we filter less than we should be. And so if our flow rate here is low, or our osmolarity is low, they usually go hand in hand, then what we want to have happen is GFR to go up. And to do that, we need blood pressure to go back up. And okay, so we can follow through on sort of localized effects that will help maintain that GFR. And the big one will be the afferent arteriole will dilate, will open up, so that the pressure here will rise. That's solving our fall in GFR problem. But it's not solving our blood pressure problem, right? So we have the macula densa also tied to stimulating the JG cells, increasing renin, and off we go to, right, and again, the broad picture here, increases in total peripheral resistance and indirectly blood volume that's going to boost our blood pressure. Okay, now, and again, just as an aside, not really an aside, but in terms of that regulating GFR, angiotensin II very specifically constricts the efferent arteriole, right? So we had the macula densa through a paracrine mechanism dilating the afferent, that boosts the pressure here. But if we constrict the efferent, that also boosts pressure here. So you really want to do both, which is exactly what happens due to what this macula densa is doing, right? So the macula densa is actually involved in autoregulation, paracrine dilation of the afferent, and endocrine regulation, constriction of the efferent through renin and angiotensin II production to make GFR goes up, okay? Back up. Now remember, we need to fix the systemic blood pressure problem too, right? And so our angiotensin II is not just going to constrict here, but it's going to constrict everywhere, right? And so now we can follow through and list our angiotensin II effects, right? And so we get an increase in total peripheral resistance, and that is essentially because of vasoconstriction. angiotensin 2 is the most potent endocrine vasoconstrictor. Right? There's a couple paracrine vasoconstrictors that are more potent. They're stronger. They work at a lower dose to generate as much or more constriction. Endothelin is what jumps to mind. But as a hormone, angiotensin 2 is the most potent vasoconstrictor and therefore the most potent hormone at affecting total peripheral resistance and blood pressure. Now, okay, so that's direct, right? Our increase in vasoconstriction is going to directly increase our blood pressure. Now, we also get an increase in both ADH and aldosterone. And as I said before, I'm gonna follow up with the actions of those in a separate video, but big picture here. Right, so we already know about ADH. ADH is a posterior pituitary neural hormone, right, released by the hypothalamus at the posterior pituitary. Again, we'll get into the stimuli for that outside of angiotensin 2. Aldosterone comes from the adrenal cortex. It also has other stimuli besides angiotensin 2, even more potent stimuli than angiotensin 2. But these two guys, generically, again, without the details here, cause an increase in tubular reabsorption. And they do so largely at the distal nephron, DCT and collecting duct. Aldosterone largely at the DCT, ADH actually at both. And again, without mechanisms right now, they cause an increase in reabsorption. Well, about 25 liters per day make it to the DCT, right? We already went down from the 180 that was filtered. In other words, we reabsorb a lot in the early nephron. But 25 liters a day, well, that's an enormous volume, right? So the point here is that if we adjust that rate of reabsorption, we can adjust our plasma volume dramatically. Plasma volume equals about 3 liters, right? So we could do a 5% tweak on, you could do a 1% tweak, but a 5% tweak on what you reabsorb at the DCT and collecting duct. 5% of 25 liters is significant, right? And so it, again, it's very significant relative to what our total plasma volume is, right? So if our plasma volume is to go up from 3 to 3.5 liters, that is a big jump in plasma volume. And again, it's going to change CVP and venous return and blah, 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 cardiac output. So it's a big deal to change our urine volume and therefore change our blood volume, right? And so these guys, we can actually put it in that sort of format. These guys decrease urine volume, which increases blood volume, right? And so our blood volume goes up, and we're back into this picture, this sort of flow diagram up here. Now, one other thing that angiotensin 2 does pretty effectively is it stimulates thirst, and it stimulates salt intake. They call it salt hunger, right? Your sort of drive to eat salt in your diet. And it does that by acting at what's called the SFO, the subfornical organ. So the subfornical organ is a region of the brain stem that is accessible to hormones. There's actually a fairly porous blood-brain barrier right there. And so circulating hormones can actually have access to brain tissue at that site. And there are receptors there for angiotensin 2 that are linked to thirst and salt intake. And so, of course, we want to increase thirst and increase salt intake. The increased salt intake will actually cause us to retain more water while we osmoregulate, right? We want to bring that, if you eat more salt, we want to bring that would make your osmolarity go up. So to counteract that, we would be thirstier and retain more water, which of course is going to make blood volume go up, right? And so we get increased H2O and NaCl intake. And again, of course, those two I can link right back here to an increase in blood volume. All right, there's angiotensin 2, how it's stimulated by low blood pressure, by changes in the tubular fluid content and flow rate, which are going to change because of our driving pressures changed, right? If our blood pressure changes. And then how it acts to sort of reverse that drop in blood pressure by both vasoconstricting and then increasing blood volume through the action of other hormones and stimulating brain centers focused on salt and water intake.